The next question of lead code biweekly contest 120 is count the number of incremovable subarrays. So basically the problem statement of this is exactly similar to the first problem, but only difference is the constraints here. So let us quick see as a just what the problem requires. Basically we are given a array called numbers. So in this we have some integers given, let's say 8. So this way we are given some integers. Now we should say how many incremovable subarrays of the given array are there. So basically a incremovable subarray is something which, let me represent the subarray of nums as nums of L colon R. So assuming L and R both are inclusive. So now from nums array, if I remove this nums of L colon R subarray, whatever resulting numbers are there, without changing the order, concatenate them, then the concatenated result should be strictly increasing. Then we say the given array is incremovable. That is, if we remove the given subarray, the concatenated part should be strictly increasing. So let's see one small example of such a subarray. So for that, let me take the example as. So now in this case, one of the incremovable subarrays is this. That is, if I number them zero based, subarray 1 2 is incremovable. As if we remove this subarray, the array resulting array that we get is 1 4 and 7. If we look over, this resulting array is strictly increasing, right? So that is why this is called incremovable subarray. So we should basically count how many incremovable subarrays are there in this, just like how we did in the first problem. But the only change here is constraints. So if you look at the constraints, in the first problem, the length of nums array was 50, but here the length of nums array is 10 power 5, and value of nums can be in the range 1 to 10 power 9. So let's see how we can solve this. So basically to solve this, let's consider the following example. So here basically let's see what we can do. Firstly, let us maintain how many in the prefix, how many are strictly increasing. So if we look over in the prefix till here, we can find out all the values are strictly increasing, right? Why? Because firstly, let's make some observations. So what happens when we basically remove a sub array of the given array? So let me write it in terms of a values. So until a minus 1. So what happens when I remove a subarray from this? We can observe that if we remove a subarray of starting index L and ending R, then that particular subpart gets removed away, and some part of prefix and some part of suffix of the array will get concatenated, right? So if that is the case, then we can observe that for sure whatever prefix part that is getting concatenated, that should be strictly increasing, and the suffix part that is getting concatenated should be strictly increasing, and the end point of prefix should be smaller than the start point of the suffix block, right? Then we can say the concatenated part is strictly increasing. So if we write it in terms of conditions, firstly for any subarray that we remove, prefix part that got concatenated should be strictly increasing. Suffix part that that we are concatenating should be strictly increasing. And endpoint of the prefix, so let me denote it as end of prefix should be smaller than a of start of suffix, right? So if these three conditions hold, then we can say for sure the given subarray is incremovable. That is, after removing this subarray, if this is holding true, all these three conditions, then this particular removed subarray is incremovable. So now what we are doing is we are trying to find out how many such subarrays are there. For that, to do it in an efficient way, we can first find out what is the prefix that is strictly increasing. Right? Why? Because we just saw that for sure some prefix of the array and some suffix of the array gets concatenated. So in case if there is a prefix, if we consider this prefix, this particular value is not satisfying, is violating the given, is violating the first condition. So that means we can't pick a subarray whose L is greater than this and R is anywhere, because this prefix itself violates the condition, right? So for that, we are finding out the longest prefix firstly, which is strictly increasing. And for every suffix, we'll search for the prefix, the longest prefix that we can take. But here there can be one issue, that is if we are picking the prefix and suffix, if we are considering the prefix and the suffix, at a point suffix and prefix can intersect. We can observe that intersection of suffix and prefix will occur basically if we find the longest prefix which is increasing and longest suffix which is increasing. These two will only intersect if the complete array is strictly increasing. Right? This will only intersect, these two will intersect if the complete array is strictly increasing. If the complete array is strictly increasing. So intersection of prefix and suffix we can handle. Now, if the complete array is not strictly increasing, we can for sure guarantee that there will be for sure guarantee that longest prefix that is increasing will never intersect longest suffix that is increasing, because there will be one such number which will violate for prefix and violate for suffix. So that is why uh, so just to handle the intersection case beforehand, if the complete array is strictly increasing, the answer is just length of the array into n plus 1 by 2. So this is when the complete array is strictly increasing. That is because every subarray will be incremovable, right? Because the complete array itself is strictly increasing. So this just means number of L and R points that we can fix in the array. So that is what this means. Number of ways we can choose L and R. So now we know that prefix and suffix intersecting case is already handled. Now let's see the non-intersecting case, how we can solve for the non-intersecting case. So for that, let us consider this example. So let me write out the same example here, and we can look over how we can solve this using this. So we'll be doing uh, the following. We'll be doing the following calculation on this example, and it holds for every array. So if it's working for this, then it should hold for every array. So such an example is taken in this. So yeah. So now let us number them, the indices of this. So zero base, there are 0 to 10 indices. Now let us firstly find out the longest prefix, which is strictly increasing. Now we know that this particular prefix is strictly increasing, right? So now, what are the combinations that we can have? First combination is empty suffix. So for each strictly increasing suffix, we are finding out the longest prefix that can pair up with that suffix, right? So that if you know the longest prefix which can pair up, we can see that this prefix is monotonically increasing. That is, it's strictly increasing. So if some value, if some longest prefix can pair up with the current suffix, then obviously prefix with smaller length can also pair up because the values are strictly increasing. So if higher value can pair up with the starting index of the suffix, then lower values can also pair up. Right? So now for a empty suffix, the longest prefix that we can have is 1, 2, 5, 12. Right? So this is the longest prefix that we can have. That means for a empty suffix, number of prefixes that will satisfy the current suffixes, we can say it is n, we can say it is length of prefix, number of prefixes plus 1. So number of prefixes here are 1, 2, 5 and 12. So first prefix can be 1, then 1, 2, then 1, 2, 5, then 1, 2, 12, 1, 2, 5, 12. So number of prefixes which will satisfy are 4 plus 1. And why we are doing this plus 1 is we should even include the empty prefix, because even we can even remove the complete array, because complete array itself, complete array is also subarray of the given array. So that is why we consider empty prefix also. So in total there are 4 plus 1 choices. There are 4 plus 1 uh, incremovable subarrays. That is r is fixed to this. We can consider like r is fixed to this point, and L can be fixed to this one. L can be over here 2. L can be over here 3. L can be over here 4. L can be over here 5. So in total there are 5 incremovable subarrays which will satisfy the given criteria. So basically we are just fixing a suffix, assuming r is pointing before, r is pointing one step before the suffix, and we are finding out for that particular fixed suffix how many else will satisfy the given condition. So these are the set of else that will satisfy if we consider empty suffix. That is, this is an empty suffix which is left, and till here r is. So now for an empty suffix, it was straightforward. But now let's see, if we consider a suffix, then what happens? So now for suffix 14, single number is strictly increasing. So suffix 14 is a valid suffix. Now for this suffix, what is the longest prefix that we can get? So if we look over 1, 2, 5 and 12, this can be the longest prefix that we can get, right? That is because if we merge these two things, then 12 will be smaller than 14. So that means the merged result of prefix and suffix will also be strictly increasing. So for suffix 14, there are again 4 plus 1 choices to pick L. So there are 5 here, there are 5 choices over here. So now to find out till which point in the prefix, to find out the longest prefix, what we can do is we can binary search we can binary search for the smaller value, considering the endpoint of the suffix. Basically, if we consider 14 as the suffix, starting point of the suffix is 14. So in the prefix values, the endpoint which is smaller than the starting point of this, to find the endpoint which is smaller than the starting point of the suffix, we can binary search. So longest prefix has these elements. Among these, 12 is smaller than 14. Right? So the longest suffix is 4. The longest prefix is 4 plus 1 because we include empty also, empty prefix. Now similarly, let's see what will be the value for suffix 13 and 14. If the suffix is 13 and 14, then the longest prefix which can be merged is this. So the value for this is 4 plus 1 again, which is 5. There are 5 choices to pick L if R is fixed. Now for the suffix 10, 13 and 14, we can see that the suffix starting point is 10. So we can't pick prefix 1, 2, 5 and 12. Why? Because if we pick 1, 2, 5 and 12, when we merge them, 12 is greater than 10. So that is why we can't pick 1, 2, 5 and 12. So the longest prefix which will satisfy the conditions would be 1, 2 and 5. So to find this longest prefix, just like we discussed, we can binary search in the prefix area. That is among all the indices which are contributing to strictly increasing prefix, we can find out the one whose value is the index whose value is smaller than 10, because we know as the prefix is strictly increasing, it's monotonic. So for this, number of choices we have are 3 plus 1. That is, there are 4 choices for this. Now for a suffix which is 5, 10, 13 and 14, 13 and 14, the suffix, the longest prefix that will satisfy the conditions are 1 comma 2. We can get this by binary searching. So if we concatenate them, we can see that they are strictly increasing. So number of ways we can choose else would be 2 plus 1 in this scenario. That is, possible there are three possible incremovable subarrays for this fixed suffix. Now let us fix the suffix as 3, 5, 10, 13 and 14. So for this fixed suffix, we can see that the longest prefix that will satisfy the criteria is 1, 2. So that means there are 2 plus 1, which is 3 choices. That is, there are 3 incremovable subarrays. That is, one of them is, this is our suffix. We can fix our here our L will be, because our fixed suffix is this. So if we fix our L over here, then we can see that concatenation of this prefix and this suffix will give us a strictly increasing sequence. Similarly, we can fix L over here and we can fix L over here. So there are 3 choices to fix L. If we fix L over here, it means we are picking empty prefix. If we are fixing L over here, that means we are picking a prefix which has value 1 in it. If we fix our L over here, that means we are picking a prefix whose value is 1, 2. So there are 3 choices. Now let us look over. For the next suffix, if we look over, so for the next suffix, if we look over, this is our suffix. Now, before finding the longest prefix for this, if we look over, this suffix itself is not strictly increasing. That means it's violating the given conditions. So the conditions that we broke down is prefix should be strictly increasing, suffix should be strictly increasing, and the merged part should be strictly for the merged part to be strictly increasing, prefix should be strictly increasing, should be strictly increasing, and end point of prefix should be smaller than starting point of suffix subarray. So here, if we see, this suffix itself is not strictly increasing. So from here we can stop. We can stop fixing the suffixes. So from this we can see that in total number of incremovable subarrays are, for the first fixed suffix there were 5, second fixed there were 5, for the third fixed there were 5, plus for the fourth there were 4, for the fifth there were 3, for the sixth there were 3. So in total there are 19, 22, 25. In total there are 25 incremovable subarrays. So hint of implementing this would be just find out the longest increasing prefix firstly. Now we know that what is the longest increasing prefix as of now. So we can make use of that fact to binary search, because we know till the current point all elements are strictly increasing. Now we can iterate from back. For empty suffix we can find out the longest prefix. Similarly for uh, the suffix with one value, what is the longest prefix? Suffix with two values, what is the longest prefix? So to find out the longest prefix, as discussed, we can fix this 13. If the fixed suffix is 13 and 14, we can fix 13, and in this search space we can search for the we can search for the highest index whose value is smaller than 13. For that we can binary search, because this prefix is monotonical. That is, it's strictly increasing, so we can binary search for that. And similarly for 10 we can find the same, for 5 we can find the same, and for 3 we can find the same. So this way we can solve the problem. So if we look over the time complexity, as we discussed, the implementation, for every fixed suffix we are binary searching in the prefix. So if n is the length of our array, in the worst case we can say we'll be performing big O of n into log n computations. As for every fixed suffix we are binary searching in the prefix. So we can say the time complexity is big O of n into log n, log 2 of n. And this can even be brought down to big of n also. It depends on how you implement. If you use binary search to find the smallest element, uh, to find the smallest element in the prefix for a fixed suffix, then it becomes n log n. Whereas instead of binary search, we can even apply two pointer. So if we use two pointer, because both are already sorted, we need not sort the suffix and prefix. As they are already sorted, we can just use two pointers, one pointer in the suffix. Like we are moving the suffix, however. So for every fixed suffix, we can maintain one more pointer in the prefix and move that pointer according to the equalities. As both the sequences are strictly increasing, this is strictly increasing sequence, increasing sequence. So for a fixed I here, we can come from back and we can find out we can move a pointer and find out the longest index whose value is smaller than this I. Then when we move this pointer downwards, we can start to find the smallest element in the prefix which is smaller than the current start index of the suffix. We can start our pointer from this point itself instead of starting from the starting point. As as if for a higher value, this is the smaller index, this is the smaller value, then for a smaller value, for sure the higher values can't be smaller. So definitely the lower value should only be smaller. So with this relation, we can just move the pointer from here itself. So because we are just moving the pointers, it would become, we could implement this in big of A. So this way we can solve the problem with either two pointer or binary search. And if we look at the space complexity here, it depends on how you implement. So we can implement it considering an ideal situation. We can implement this with a space of big of 1. All these are per test case. So this way we can solve the problem.